Let's consider another way to prove that the least squares regression solution is x transpose x inverse x transpose y. That's beta hat. Okay, so recall our y was an n by 1 vector, our x was an n by p full rank matrix, and we want to explain the variation in y with linear combinations of the columns in x, and we're going to do that by minimizing the distance between the observed y and the fitted y. I'm going to need some notation, so let me define h of x to be x transpose x inverse x transpose. Okay, so a couple things to note about h of x. One is h of x is symmetric, and then two is that it's idempotent. Another interesting fact is that I minus h of x, notice that it is both symmetric and idempotent as well. Okay, and then finally, notice that I minus h of x times any linear combination of the columns of x, let's say x times a, is 0. So it's easy to see that. I think you just take I minus x transpose x inverse x transpose times x times a. If I multiply x times that x transpose, I get x transpose x, but there I have an x transpose x inverse, so that's just I. And then when I multiply this x times I just get x, so I get x minus x, which is 0. Okay, so we need those facts. So I'm going to need this room. Now, I'm going to try to minimize my least squares criteria. So let me just add and subtract an x beta hat. That then is going to be equal to the norm of y minus x beta hat squared plus 2 y minus x beta hat transpose x beta hat minus x beta plus norm x beta hat minus x beta squared. This final quantity is always positive because it's a norm, a squared norm. So I'm only going to make it smaller by getting rid of it. Now, let me just look at this term right here. So that's 2y minus x transpose x inverse x transpose y times x beta hat minus x beta. So this quantity, oh, and that's transposed. This quantity right there, I can do the following. I can pull out a y and get I minus, and then this quantity right here I've been calling h of x, I minus h of x, and then transposed. But remember, both I and h of x, not h of y, h of x are both symmetric, so the transpose is irrelevant. So I can write that as 2I minus h of x, and then over here looking at this term, I can pull an x out and I get beta hat minus beta, okay, plus y minus x beta hat. Okay, then recall, if I take I minus h of x and I multiply it times x, I get 0. So this whole term right here is 0. So I get norm y minus x beta hat squared. So what we see is that for any arbitrary beta, the difference between x beta hat and y is strictly, or is greater than or equal to the norm if we plug in the specific value of beta hat. Therefore, beta hat must be the minimizer.